大家好，我是清华大学电机系黄颖健。之前我们介绍了waveguide，介绍了 resonant cavity，但是呢，今天我们在这个第16个章节里头呢，会介绍一个新的元件，叫做 antenna，也就是天线。但是呢，在这一章里头我们介绍天线还是最基本的，叫做 dipole antenna。So in this lecture, we're going to analyze dipole antennas and also introduce you a few relevant parameters to characterize an antenna. The first part of the lecture is going to be a few basic concepts, and then we'll start to analyze a very simple electric dipole antenna called Hertzian dipole antenna. After doing this, we're going to move into a topic that is relevant to magnetic field, oscillating magnetic field generating radiation. And this is a magnetic dipole antenna. In section 16.4, we're going to talk about a few antenna parameters which are useful to describe the performance of an antenna. And finally, we'll have a review. So the section 16.1 is going to give you a few basic concepts. If you still remember in lecture 2.1, electromagnetic 2, I show you this transmission line network. It starts from a generator, and there's an impedance inside this generator. The signal is transmitted to a load for some applications through some transmission line. And this transmission line could be an electric cable or some waveguide. And you saw this before. I put a device here to tell you that the electromagnetic wave can be radiated into space. And this device is called the antenna. If you run the process backward, then you can receive electromagnetic radiation through this antenna and transmit this signal to a receiver circuit for some analysis or for some applications. So an antenna is a device which transmits electromagnetic radiation into space or receive electromagnetic wave from space. So this is the big picture about an antenna. Suppose that we have a transmitting antenna. The wave is going to radiate into space. So if you detect this radiation from far away, this antenna is going to more like a point in space. So usually we're going to use spherical coordinate system to describe the field radiated by an antenna. And in the next few sessions, we're going to focus our discussion on transmitting antenna, and later we'll talk about receiving antenna. And of course, if you want to know the field radiated into space, we need to have some mathematical tools to analyze it. And the first step to analyze the radiation field into space is that suppose we knew the current on the antenna, and then we can use this formula to calculate the vector potential generated by the current element in the antenna. Once we have the vector potential in space, then we can proceed with the second step to calculate the magnetic field through this curl of A formula. And the Ampere's law connect the electric field and magnetic field through this formula. So if we know the magnetic field from curl of A calculation, we can also deduce the electric field through this curl of H calculation. So in general, we go through this step 1, step 2, and step 3 to figure out all the field, the electric field and magnetic field in space. Then once you have the electric field and magnetic field, you can calculate the average power by using this complex Poynting vector. So this is the general steps to analyze an antenna. Now let's look into this very simple example as the antenna. suppose in space we have a small dipole. The separation of these two charges in the dipole is much less than the wavelength. So this means that the current is not going to be a spatial function. It's not going to be a function of space along these elements. So we can just quickly write down this current that only depends on the time. So this kind of antenna is called Hertzian dipole antenna, and we don't take into account the spatial phase of the current along this dipole axis. And the current is the oscillating charge. So if you do an integration of the current through time, you'll be able to calculate the charge on this small piece of the current element. And we specify this problem with a harmonic variation on the charge and current. So this is a harmonic signal. So we can use a phasor expression to analyze this problem. So given this phasor expression, you can also relate this charge to the phasor of the current. And so the phasor of the charge is going to be equal to the current divided by j omega. And then you multiply this exponential j omega t and take real part of it to get the real function of the charge. And because of this differentiation and also integration relationship between charge and current, so you expect that the phase between the current and also charge will differ by 90 degrees because of this J underneath of this I. So this means that when the charge oscillates along this direction and the current will stop at this tip, so the charge will accumulate to the maximum value. So the maximum value of the charge is going to be the minimum value of the current. And this is the physical meaning of this 90-degree hour phase between charge and also the current. And don't forget that if you have a charge plus Q and minus Q here separated with some distance, then you can describe this arrangement as an electric dipole, which is the charge multiplying with the separation of the charge. And this dipole expression is going to be important when we talk about the field radiated from such a dipole antenna. And by the way, if you have a antenna length that is much less than the radiation wavelength, we call such a antenna to be a Hertzian dipole antenna. Now let's start to analyze the radiation from such a very teeny antenna. The step one is to write down the vector potential as a function of current and do integration over the source. And then you can derive an expression for the vector potential at a distance r from the source. So we pick up this formula and then do the integration, because the current is not going to be a function of distance on this dipole antenna. So this integration is very simple. You just take out everything to outside the integration sign, and then just write the dV prime as a volume occupied by this current element, and then you'll be able to get this result. Because the current is along z direction, so the vector potential is also along z direction. But don't forget that we analyzed an antenna problem inside a spherical space. Therefore, we have to convert this unit vector along z into unit vector along r and also theta for the spherical coordinate system. And once we have the vector potential, then we are in the position to calculate the magnetic field through this 1 over mu curl of A. So just put this expression into this formula, then you end up having this expression for your magnetic field. And I also told you that for step 3, we're going to use the Ampere's law to connect the electric field to the magnetic field. So on the last page, we have the magnetic field. So we put the magnetic field into this curl of H, and then divide the whole thing with j omega epsilon 0. Then we'll be able to derive the electric field along all directions, theta direction and phi direction. And the specific form of the expression are given here. Turns out that there's no phi direction electric field. That is because the dipole is axially symmetric. Therefore, along phi direction, you don't have any electric field. And this expression a little bit tedious. You have terms with the 1 over beta r, to the power of 1, to the power of 2, to the power of 3. And so we're going to divide the discussion into near field zone and far field zone, depending on which terms are significant. For example, if the beta r is much larger than 1, this means that we're looking into the location where the distance is much larger than the radiation wavelength. Then this term is going to be more significant, because with a higher power and with a large value of beta r, this term is going to be much smaller than this term. So we'll just keep this term for our discussion. We call this as a far field zone when the distance is much larger than the radiation wavelength. On the other hand, if we look into a location where the distance is much less than the radiation wavelength in the near field zone, then this term is going to be more significant, because when this beta r is very small compared to 1, this term is going to be much larger than this term and also this term. So we're going to separate the problem into the far field zone and also the near field zone, and try to understand the physics associated with the Hertzian dipole antenna. 所以呢，在这个第一小节里头，我介绍了几个基本的观念。那一个天线呢，就是用来传输或者是接收电磁波的一个元件。那我们经常是用这个圆坐标来描述，因为一个天线在空间里头呢，我们预期它会把讯号传到很远的地方去，或者是讯号从很远的地方过来，所以呢，这个天线在整个空间里头看起来像是一点一样。那我们通常有3个步骤来分析这个天线的场的这个计算。那第一个步骤呢，就是先把天线上头的电流呢拿出来算这个在空中的这个有关的 vector potential 的场。你一旦把这个 vector potential 从电流算出来之后，就可以呢用它来算磁场，因为磁场呢是vector potential 的这个curl operation 所产生出来的一个量，所以呢 B 等于 curl A 这个公式可以拿来用。那第3个步骤呢，就是一旦你有磁场之后，你可以用 Ampere's law 把这个电场算出来。所以这是第一个小节里头呢跟各位介绍的几个重点，谢谢。